Hi everyone, and welcome to another seminar of Physics Latam, starting this new year, 2026. Today we are very happy and honored to have Professor Fröhlich with us. He's a professor emeritus at ETH Zurich, and now he is retired. He has made many important contributions in theoretical physics, including field theories, statistical mechanics, and quantum mechanics, as well as proposed a solution to the measurement problem in quantum mechanics, which we'll be covering today in today's talk. He has numerous awards, including the Danny Heinemann Prize, the Marcel Benoit Prize, the Max Planck Medal, and the Henry Poincaré Prize. Please remember to raise your hand at any point if you have any question. And now I'll leave you with Professor Fröhlich. Please go ahead.
All right, so it's a pleasure to give this talk. If there are urgent questions, please feel free to interrupt me. But certainly at the end of the talk, we can have a question session. So this talk will be about quantum mechanics, and let's just see what we will cover. I will present the critical analysis of the notions of events, states, and evolution in quantum mechanics. The purpose will be to unravel the quantum mechanical time evolution of isolated open systems. And in order to do that, I will identify a fundamental mechanism of dissipation, of mixing, if you like, which is at work in systems of matter coupled to the quantized electromagnetic field. And I will only discuss this in the non-relativistic limit, namely in a limit where the velocity of light tends to infinity, because that's simpler than the relativistic version. The mechanism responsible for dissipation is dubbed principle of declining or diminishing potentialities. When it is combined with a state selection postulate, it yields a precise law for the stochastic time evolution of states of individual isolated open systems, which supersedes the Schrödinger evolution. This law furnishes a precise description of many phenomena, for example, the fluorescence or spontaneous emission of photons by atoms, and it also yields a solution of the measurement problem in quantum mechanics. At least that's what they claim. My work has been done in collaboration with various people, some junior people, and also a colleague more or less of my age, Philippe Blanchard. And I thank the organizers of this series for inviting me to present this talk. So here is a table of contents. I will briefly talk about the need for completion of quantum mechanics. Then I will discuss something that is a little analogous to what's going on in quantum mechanics, and that is the theory of diffusion and of random walks. And then I will talk about events and the principle of declining potentialities, then about states and the state selection postulate. Finally, I will derive the stochastic evolution of the individual systems in quantum mechanics, and there will be a short outlook. And on the portraits you see on this slide are the sort of big people who created quantum mechanics: Heisenberg, Dirac, and to a lesser extent Schrödinger. In fact, Schrödinger contributed a lot to confusing things, as we will see. So, quantum mechanics appears to be afflicted by a curse. Most people who use it in their daily work are unable to coherently describe its meaning. For example, to say what is meant by events and to explain how events arise. For example, to explain how a successful measurement of a physical quantity should be described in quantum mechanics, or to understand the fluorescence of atoms, the decay of unstable nuclei, or the appearance of particle tracks in detectors. They view quantum mechanical time evolution as linear and deterministic, But then they claim that quantum mechanics is fundamentally probabilistic, as first suggested by Einstein in his work on spontaneous and induced emission of photons and absorption of photons by atoms, and then by Born in 1926. These seemingly contradictory features of the theory have given rise to a plethora of so-called interpretations of quantum mechanics: Copenhagen, many worlds, cubism, relational quantum mechanics, most of which is nonsense. In fact, I claim that the theory that needs 20 different interpretations is probably a theory that hasn't been completed. And so this talk will be about a proposal for how to complete quantum mechanics so that these contradictory features that appear to exist will disappear. And in fact, the completion of quantum mechanics I will sketch is what I've been working on during the past 12 years or so. All right. In textbook quantum mechanics, people say the time evolution of states should be described by a Schrödinger von Neumann equation, or if dissipative processes are at work, by a Limplot-type evolution equation, unless a measurement is carried out, which will then cause wave function collapse in accordance with Born's rule. There are various descriptions of measuring processes due to Born, von Neumann, and Lüders, but they all seem to be very much ad hoc. So measurements are dynamical processes too, and they involve interactions between a small system of interest and a large system representing an apparatus that can perform measurements. So one would expect that it is possible to describe the evolution of the total system, the composition of the small and the large system, by a Schrödinger von Neumann equation. At least that's what one would expect if the Schrödinger von Neumann equation were as fundamental as people usually believe. Now, what appears to be correct is to say the following. In quantum mechanics, states averaged over a very large ensemble of identically prepared physical systems, I call them ensemble states, evolve in time according to a linear deterministic law. But states of an individual system belonging to this ensemble, they evolve according to a nonlinear stochastic law of dynamics. The nature of this law is the subject of various controversies, and it is the subject of this talk. I will, in fact, suggest a very specific form of this stochastic law that describes the dynamics of states of individual systems. Now, in order to sort of introduce you to the way I think about these problems, it is probably a good idea to describe a simpler problem, and that's the problem of diffusion and random walks. So I consider an ensemble of non-interacting particles hopping on a lattice Z nu. Nu is the dimension, and they're subject to thermal noise, so they sort of stochastically hop around. The ensemble state, namely the state of a large family of such non-interacting particles at time t, is given by the density rho sub t of particles in this gas. The time evolution of the density rho sub t is usually described by the diffusion equation. It might be a diffusion equation with drift, but let's forget about the drift for the moment. The diffusion equation is dissipative. In fact, it's an equation that describes entropy production. But it is a linear and deterministic equation. And you see it in Formula 1. The dot, of course, is time derivative. Rho dot t of x is the diffusion constant. times the discrete Laplacian applied to rho t evaluated at the point x. So I will now try to find out what kind of stochastic motion of an individual particle, denoted by psi, in the gas implies that the time dependence of an ensemble state, rho sub t, is given by the diffusion equation that you see in Formula 1. The solution of this problem comes by unraveling the diffusion equation. And I will now explain to you what unraveling means. Before we do that, the ontology behind this problem is the following. I guess nobody doubts that the true state of an individual particle psi at an arbitrary time t is a site x sub psi of t in the lattice, namely its position at time t. You cannot specify a momentum because we look at the discrete system. So, classically, the state of such a particle is simply its position. This corresponds to a density rho sub t given by a conical delta function located at the position x sub psi of t of the particle at time t. This is a pure state because it cannot be written as a convex combination of other states. It's really a pure state in the literal sense of this word. Now, during a time interval from time t to time t plus dt, dt is a small but positive time step, a particle psi may either remain at its position x sub psi of t, or it may jump to a nearest neighbor site y, given by x sub psi t plus a unit vector delta in the lattice. Usually, if dt is small enough, the probability of seeing two or more jumps is extremely small. It's of order dt squared, which when dt becomes small can be neglected. So you just look at the two possibilities that the particle either stays where it is in this interval from t to t plus dt, or it makes a nearest neighbor jump. The probabilities for staying where the particle is at time t is given by p node jump, and this is given by 1 minus 2 times the dimension of the lattice times the diffusion constant times dt. That comes just by inspecting the right-hand side of equation 1. It's very simple to see this. And the probability to make a nearest neighbor jump is simply given by diffusion constant times dt. So that's what you can get by meditating the diffusion equation. This is a Poisson jump process. It's a discrete version of the Wiener process of Brownian motion. This law 2 for the stochastic motion of an individual particle psi implies that when we take an average over the positions of all particles in the gas, then the time dependence of the density of particles is given by the diffusion equation. So you can go forth and back between equations 1 and equation 2. Equation 1 is the time evolution of ensemble states, and equation 2 prescribes the stochastic evolution of individual particles in this gas. Now, a trajectory of a random walk or of a particle is described by a simple random walk, namely, if it makes n jumps, you have to specify n sites in the lattice that are nearest neighbors. That you just have to make nearest neighbor jumps to travel along. So little n is the number of jumps the random walker performs between an initial time, which we may choose to be 0, and the final time t positive. Let's imagine that the particle psi makes nearest neighbor jumps in each time interval of times from Tj to Tj plus ddTj, where T1 up to Tn is an n-tuple of times ordered according to their size. So we imagine that the particle traces out the random trajectories with jumps at these times T1 up to Tn. Now, according to law 2 that we saw here, we can calculate the probability of seeing such a random trajectory, and it is given by this next formula, which specifies the probability of seeing a trajectory, psi, underlined with jumps at times t1 up to tn. You see that the probability for not jumping from the site where you arrive, say at the time tj minus 1, for a time difference tj minus 1, decreases exponentially in this time difference. So at some point, the particle definitely will want to jump. Now, the formula for this probability is a lattice analog of the Wiener measure in the theory of Brownian motion. It can be used to predict many properties of the stochastic motion of random walkers. For example, it can be used to immediately calculate the average distance a random walker travels in a time t. The expectation of the square of the distance the random walker travels is seen to grow linearly in time t. And that's really a consequence of the form of this lattice analog of the Wiener measure. So obviously, linear rise in the square distance is typical of diffusive motion with entropy production. So let's draw a few conclusions from this discussion. The states of a large ensemble of random walkers, which I call ensemble states, evolve linearly and deterministically according to the diffusion equation, but this dynamics is dissipative, entropy is produced. It's an easy exercise to show that the entropy of a density of random walkers grows in time if the density evolves according to the diffusion equation. Now, this entropy production is actually the fundamental reason why the states of an individual random walker evolve stochastically according to this Poisson jump process that is determined by law 2 that we saw. I would like to sort of jump ahead and introduce the notions events, trees, and histories, which will be important in my discussion of quantum mechanics. In this example of diffusion and random walks, an event is the arrival at some time t of a random walker at a certain position x sub psi of t in the lattice. What is a tree? A tree is all possible random walks on the lattice with a fixed initial position. What is a history? A history is a specific random walk realized in some interval of times. So we will see analogous notions in quantum mechanics in just a minute. The path space is the space of all possible random walks with a fixed initial position. The reality is a random walk actually observed, for example, under the microscope. In other words, it doesn't make sense, since random walks are stochastic, it doesn't make sense to claim that there are many worlds that all exist. There's only one world, but unfortunately the world of these random walkers is such that you cannot really predict the future, but you can only predict probabilities of certain events happening in the future. The dissipation or entropy production of random walks can also be expressed as follows. Denote by f sub greater or equal to t the algebra of cylinder functions that only depend on positions of random walkers at times greater or equal to t. Then these algebras functions sit inside in one another, and they sit inside one another properly, namely they really become smaller. All right, so these are some lessons that I suggest you try to keep in mind, because we will encounter analogous properties in quantum mechanics. So I will now talk about events and the principle of declining potentialities in quantum mechanics. I will discuss, as I already mentioned, non-relativistic quantum mechanics, which arises when the velocity of light tends to infinity, because then we have very precise results. The relativistic version is still somewhat tentative. And I will present the so-called ETH approach to quantum mechanics, E standing for events, T for trees, and H for histories. And I will try to stress, at least in words, the analogy between quantum mechanics and the theory of diffusion and random walks that I just sketched. So here are the basic elements of the ETH approach. Potential events in an isolated open system S. What does it mean for a system to be isolated and open? Isolated means that it has only negligibly small, weak interactions with the rest of the universe. Open means that it can release, for example, photons or gravitons to the outside world. So such systems are described, potential events in such systems are described by partitions of unity, by mutually disjoint orthogonal projections. I denote them by pi hat sub xi. Xi is an index, and these projections have finite rank, at least in the non-relativistic regime, and the index set is called the spectrum of the event, and it is denumerable. So let E sub S be the set of all potential events possibly happening in such a system. I should say the following. You can introduce the analogous notion for random walks. Then the projections are simply, projections on two fixed positions of the random walk. They all commute with one another. In quantum mechanics, of course, projections taken from different potential events won't commute in general, and that's what makes quantum mechanics quite different in the end. So, the idea is that at every time t, there is a representation of all projections in this family E sub S by concrete projection operator. So pi hat psi in a potential event E is mapped to a concrete projection pi sub psi of t that acts on a separable Hilbert space H. The representatives of the same projection pi hat sub psi at different times are unitarily conjugated to one another, and the unitary is given by the propagator of the system. That's the Heisenberg equation for the time evolution of operators that you're all familiar with. So H sub S is the Hamiltonian of the system. So this enables us to introduce certain algebras. They are the analogs of the function algebras I mentioned before in the context of diffusion theory. So the algebra E greater or equal to T is the algebra generated by all projection operators pi of T prime. Pi of T prime represents an abstract projection pi hat in a potential event E at some time t prime greater or equal to t. It immediately follows from this definition that these algebras are nested. E greater or equal to t prime sits inside E greater or equal to t whenever t prime is larger than t. The Heisenberg time evolution that we saw on the last slide in this equation 4, 7 should be 4 here, implies that These algebras are all conjugated to one another by the unitary propagator of the system. In particular, all these algebras, E greater or equal to T, are isomorphic to the algebra E greater or equal to 0, which I denote by E sub 0 for all times T. Now comes a very basic idea, and I formulate it as a principle, and then we will try to understand why this principle is correct in concrete models of quantum theory. It is called the principle of declining or diminishing potentialities. In the ETH approach to quantum mechanics, an isolated open system S capable of producing events that you can observe from the outside. Such a system is characterized by the property that these algebras E greater or equal to T sit properly inside each other, meaning that E greater or equal to T prime is contained in E greater or equal to T, but not equal for all times T prime larger than T. So I mentioned an analogous property of the cylinder functions on random walks a few minutes ago. So this is supposedly a fundamental principle in quantum theory. It's a little surprising that I think nobody thought of it before I proposed it some time ago. So why should this principle be true? It's an expression of fundamental dissipation. It holds in theories with massless modes, in particular photons. For example, in relativistic QED, where it follows from a certain theorem by Detlef Buchholz. And it also holds in quantum optics in the limit where the velocity of light tends to infinity. So why is that? Photons and gravitons emitted in the region O that you see in my drawing can escape at the speed of light without being ever detected in the forward light cone v plus t prime above time t prime. The time axis is the world line of an observer. And so v plus t prime is the forward light cone above the position of this observer at time t prime. Photons produced in O can escape without an observer sitting at time t prime being able to ever observe them. Therefore, the energy and information these photons carry away can never be recovered at any future time. This has a mathematical expression of the following form. For a time t prime larger than t, bounded functions of the asymptotic electromagnetic field operators localized in O generate a certain subalgebra of the total algebra corresponding to the light cone v plus t that commute with all bounded operators localized in the light cone v plus t prime larger than t. In other words, with all operators in ev plus t prime. So that's sort of the general algebraic property that can be derived from the result of Buchholz. Buchholz looked at LSZ scattering of photons in QED, and along the way he proved something that amounts to what I'm saying here. In the limit where the velocity of light tends to infinity, the light cones open up to half spaces, and then the principle of declining potentiality simply says that the caricatures of the electromagnetic field arising in the limit where the velocity of light tends to infinity are represented by operators which are located in time slices, and the operators in a time slice, say between time t and t prime, commute with all the operators localized at times greater or equal to t prime. So these are facts, these are, theorems. These theorems show that in certain models of quantum electrodynamics, this principle of declining potentialities holds. And I would like to add the following comment. Apparently, as in the genesis of relativity theory, in particular special relativity, the electromagnetic field, perhaps in the relativistic case also the gravitational field, apparently play an absolutely crucial role. Fields with massless modes cause fundamental dissipation, and the way this is expressed is to appeal to Huygens principle in the form it was explained in this drawing. So without the principle of declining potentialities, information about the physical system would not be retrievable, and the measurement problem would never be solved. And that's, of course, the difficulty that people have encountered without realizing why they have encountered it, and they have debated it for 100 years without making much progress. But now I think there is progress, and that's what I'm going to talk about. So, next section, states and the state selection postulate. The third basic element of the ETH approach is a meaningful notion of states of physical systems. Clearly, a state of a system at time t ought to be a device that serves to predict the probabilities of events that actualize or are observed at times larger than t. So, that suggests the following definition of the state of a physical system at time t. A state omega of a system S at time t is a quantum probability measure on the algebra E greater or equal to t that I defined on this in equation 5. Okay, now there is a theorem due to Gleason that tells us that quantum probability measures are nothing but just normalized positive linear functionals on the algebra. In other words, states in the sense of the mathematicians. So if the algebras E greater or equal to t were independent of time t, all equal to each other, then states of such a system in the Heisenberg picture would be independent of time, while in the Schrödinger picture they would evolve according to the Schrödinger von Neumann equation. This is what would happen in a theory without photons, without massless modes. If all particles of nature were strictly massive, then the algebras E greater or equal to t would be independent of time t. This would mean that no information about such systems could ever be retrieved. So if the principle of declining potentialities holds, then states of a system at time t depend non-trivially on time t, even in the Heisenberg picture. And this is something, again, that people apparently never realized, that even in the Heisenberg picture, physical states depend on time. All right. I might perhaps add the following comment. The principle of declining potentialities might also have other explanations. For example, in a universe filled with black holes, there is definitely the principle of declining potentialities would hold too, because information can disappear between the horizons of the black holes. So, given an initial state omega naught of a system, of an isolated open system at time 0, the ensemble state omega sub t at the later time t corresponding to the initial state omega naught is given by restricting omega naught to the subalgebra E greater or equal to t, which, according to the principle of declining potentialities, sits non-trivially inside E naught. This is perfectly analogous to how the density of diffusing random walkers is defined in diffusion theory, namely by restricting the Wiener measure to the algebra of functions of positions of the random walks at times greater or equal to t. In general, the map from the initial state omega naught to the state omega t does not preserve purity. So omega naught might be a pure state, but omega t need not be pure. Why? Because E greater or equal to t is a subalgebra, an honest subalgebra of E naught when t is positive, according to the principle of declining potentialities. And therefore, the restriction of a pure state to this subalgebra need not look pure anymore. This is, of course, the phenomenon of entanglement that Schrödinger discovered in the early 30s. All right. Now I have to add a certain property that makes non-relativistic QED, namely the version of quantum electrodynamics arising in the limit when the velocity of light tends to infinity, much easier than the relativistic theory. And it's this property P. The algebra E naught that I defined is in the non-relativistic limit always isomorphic to the algebra of all bounded operators on a certain separable Hilbert space H naught. In the relativistic case, that is definitely not the case. E naught would be a von Neumann algebra of type 3-1 typically, and that makes the theory quite a lot harder. Now, since in the non-relativistic limit, E naught is isomorphic to the algebra of all bounded operators on a Hilbert space, every state on this algebra is given by a density matrix. Let's call the density matrix corresponding to the state little omega naught, capital omega naught. The isomorphism of the algebra E greater or equal to T to E naught, which is a consequence of the Heisenberg time evolution, implies that the ensemble state omega t, namely the restriction of omega naught to E greater or equal to T, is again represented by a density matrix, which I now denote by capital omega sub t. If the algebras E greater or equal to T were independent of time t, then of course in the Heisenberg picture, all these density matrices would be identical to one another for all times t. In the Schrödinger picture, the density matrix omega sub t representing the ensemble state omega sub t at time t is defined through this equation number 7. You say that trace omega t of that the expectation of an operator x in E naught in a state omega t is the same as the expectation of the transported operator x in the original initial state omega naught. Now the map U of t and 0 that maps omega naught to omega t is obviously, according to the equation we just saw, the equation 7, obviously a linear positivity preserving and trace preserving map for all times t positive. In fact, it is completely positive. I don't know whether you know what complete positivity means. It's not important. I won't explain it now. And furthermore, this map satisfies a sort of semi-group property, UTS equals UTR times URS for all ordered triples of times t larger than r larger than s. If the state of the radiation field is time translation invariant, then in fact UTS is given by the exponential of a Limblad. It's generated by a Limblad operator as written in equation 8. All right, I hope this is understandable. Now let's look at states of individual systems. The true state at an arbitrary time t of an individual system characterized by elements 1, 2, and 3, 1, and by this property the P that we saw on the last slide is given by a density matrix that is proportional to an orthogonal projection pi sub t of finite rank, generically of rank 1. If it is of rank 1, then it is a pure state. So you see, this is the same ontology as the one I proposed in the theory of random walks, where I said that the random walker at every time t sits at the specific site of the lattice, that is in a pure state. In quantum mechanics, at least in the non-relativistic theory, it is reasonable to assume that the true state of an individual quantum system at every time is a pure state, or slightly more generally, a state proportional to an orthogonal projection. All right. So let's suppose that a certain system S is in a state proportional to a projection pi t at time t. Then the ensemble state at the later time omega t plus dt, which I denote by omega sub t plus dt, is obtained by applying the Limplatt evolution to the state represented by the projection pi t. All right. Now, omega sub t plus dt is a density matrix. In other words, it is a positive self-adjoint operator of trace 1, and so you can apply the spectral decomposition. Omega sub t plus dt can be written as a certain coefficient p naught times pi naught. Pi naught is again a projection operator, plus further spectral projections of omega t plus dt multiplied by coefficients. All right. I order these terms according to the size of the coefficients. So P naught is the largest and P1 is already a little smaller, and since omega sub t plus dt is a positive operator, they are all greater or equal to 0. If the time step dt is very tiny, then the operator pi naught, the projection pi naught, is very close to the projection operator pi t at time t. All right. The potential event E represented by the spectral projections of this density matrix omega sub t plus dt actualizes, becomes actual or visible at time t plus dt according to the following state selection postulate. The true state at time t plus dt of an individual isolated system S whose state at time t is proportional to the projection pi sub t is a density matrix proportional to either the projection pi naught with a probability p naught times the dimension of pi naught, which is of the order of 1 minus order dt. dt is the time step. It's small but positive. Or it is given by one of the projections pi super delta sub t plus dt with probability p delta proportional to dt to the time step. That's the state selection postulate. Of course, it's inspired by Born's rule applied to the state that we have observed, this density matrix omega sub t plus dt. All right. So the state selection postulate says that at each time a state is selected in accordance with Born's rule. The Limplatt equation for the time evolution of ensemble states is analogous to the diffusion equation, and the state reduction postulate that I formulate here is analogous to the law 2 in the theory of random walks that determines the Poisson jump passes that I sketched. I will now ask whether we can let the time step dt tend to 0, and the answer is that that in the non-relativistic theory this is possible. So, inspired by the diffusion equation, unraveled by the Poisson jump buses, we derive a quantum mechanical stochastic law of dynamics of individual systems that can be obtained by unraveling the Limblad evolution that we found on the previous slide here on the top of the equation 8. All right, and that's the quantum mechanical analog of the diffusion. The Limblad evolution is the quantum mechanical analog of the diffusion. So we think of a very large ensemble of physical systems, all identical to a specific system S, and consisting of matter interacting with the quantized radiation field. And I only look at the non-relativistic limit where the velocity flight tends to infinity. Then, as we saw in the last section, assuming that the electromagnetic field is in a time translation invariant state, the time evolution of an ensemble state, omega sub t, is described by a Limblad equation. And that's a linear and deterministic but dissipative evolution equation. It takes the following form. Omega sub t plus dt, that's the density matrix, equals omega sub t, the density matrix at time t, plus a Limbladian applied to omega sub t times dt, plus air terms of order dt squared. The Limbladian has the following form. The first term is a commutator minus I h naught omega. H naught is the Hamiltonian of the system when it is decoupled from the electromagnetic field. And then there are additional terms that describe the emission and absorption of photons in this non-relativistic limit that lead to dissipation because of this Huygens principle that I explained. All right. Now, we have to unravel this Limblad evolution 10 in order to find the stochastic process that describes the evolution of an individual system. So, how does that go? As I discussed in the last section, the state of an individual system in this ensemble of identical systems is pure at every time t. That is given by a rank 1 orthogonal projection pi sub t, or at least proportional to a finite rank orthogonal projection at all times t. If at time t all systems in this ensemble were prepared in the same state pi sub t, the ensemble state at time t plus dt would be given by the density matrix omega sub t plus dt given by pi sub t plus the Limblad operator, Limblad generator applied to pi sub t times dt plus order dt squared. That's obvious from equation 10 that we had before. Now I do a spectral decomposition of the density matrix omega sub t plus dt. There's the form omega sub t plus dt equals p node jump times pi naught sub t plus dt plus the sum over delta p delta pi delta sub t plus dt. And these pi's are simply the spectral projections of the density matrix omega sub t plus dt. This is very analogous to what I did to derive the law for roundabouts. So Nj, the subscript Nj, stands for no jump. These spectral projections represent the possible states of an individual system at time t plus dt, selected according to the state selection postulate that I described in the last section. For simplicity, I suppose now that pi sub t is a pure state. Assuming that dt is very small, one and has the following situation. Pi naught sub t plus dt is very close to the state pi sub t at time t, and the probability p naught jump is given by 1 minus order dt. It's very close to 1. The other coefficients p1, p2, etc. are all proportional to dt, to the size of the time step, for all delta greater or equal to 1. And the sum of these probabilities, of course, must be equal to 1 because the trace of the density matrix is 1. So selecting a state corresponding to some delta positive is said to correspond to a quantum jump. Our task is to find explicit expressions for the probabilities p no jump of not observing a quantum jump in an interval of times from t1 to t2, and for the time dependence of the state pi naught sub t for t in this interval t1, t2, and for the probability of observing a quantum jump at time t2 to a state pi delta sub t2 for some delta positive that is perpendicular to the state pi naught sub t2. This problem can be solved. In fact, we have solved it completely. It's described in one of my papers, one with Gang Zhou, a Chinese colleague, and Pizzo, an Italian colleague. It's a paper that is about quantum jumps. So in that paper, we developed a somewhat novel tool of functional analysis that I call infinitesimal perturbation theory. Unfortunately, for lack of time, I cannot describe it here. It's nothing very difficult. You can look it up in my paper with Gang and Pizzo, and it can be applied to deriving the laws for the probabilities of not making quantum jumps, the p no jump as a function of time, and for the projection pi sub t, and also for the probabilities of making jumps. And here is the result. So we get the following nonlinear stochastic law of dynamics for the state of individual systems. Oops. No. Okay. Between two quantum jumps assumed to occur at times t1 and t2, the evolution of p no jump and of the state pi naught are given by the following equations. P no jump, the probability for not observing a quantum jump between times t1 and t2 is given by a certain exponential of a quantity that depends non-linearly on the state pi naught, and which is in fact always negative. So this probability, since it's is always smaller or equal to 1. And the time derivative of the state pi naught between two quantum jumps is given by a certain cubic expression in pi naught that you see here on the right-hand side. This is a totally explicit nonlinear equation for the evolution of the state pi naught between two quantum jumps. If the dissipative terms in the Limblad generator were absent, in other words, if the time evolution of the density matrix were described by a von Neumann or Schrödinger von Neumann equation, then in fact the dissipative terms in the Limblad equation are absent, and this equation 2 that you see here describes unitary Schrödinger von Neumann evolution, and p no jump would be identically equal to 1. So in other words, if you decouple matter from the quantized electromagnetic field, then meaning that there are no massless modes around, then Schrödinger evolution would be exact. But the moment matter interacts with the quantized electromagnetic field, Schrödinger evolution does not hold, but it is superseded by the laws that I'm describing here. The probability p delta to jump from a state pi naught sub t2 to a state pi delta sub t2 plus dt in a time interval from t2 to t2 plus dt for some delta positive is given by the deltath eigenvalue of a certain non-negative matrix. So it can be computed by simply diagonalizing a certain non-negative matrix. These results completely determine a probability measure on the space of state trajectories of individual systems exhibiting quantum jumps, and this measure is analogous to the Wiener measure of Brownian motion. And there is an explicit expression for this measure, which, because it's a little bit long, I'm not going to display here. That's more or less what I wanted to say about this thing. It is easy to invent, dissipative terms in equation 10 that would correspond to very explicit measurement processes. So, in other words, using this approach to quantum theory, I can certainly fully describe simple measurement processes. So it seems to me the measurement problem completely disappears. There are other problems that completely disappear. For example, Hawking's unitarity or information paradox is a misunderstanding and it completely disappears. Anyway, so that's maybe the end of the story about quantum theory. And now let's conclude with a short outlook. We have also looked at a very concrete example, namely a qubit. The pure states of a qubit interacting with the quantized radiation field are parameterized by vectors, unit vectors on the Bloch sphere, and the state trajectory of an individual qubit is described by a certain stochastic process on the Bloch sphere, which we have explicitly described in this paper about quantum jumps. Within the ETH approach, one is able to give a precise description of measurement processes, as I just mentioned, and the measurement problem evaporates. A key point is that, and that was already sort of anticipated or intuited by Heisenberg many years ago, a key point is that every measurement involves dissipation. It sort of destroys information about the state of the system previous to the measurement. So information and energy get lost in every measurement in accordance with the principle of declining potentialities. This was in fact described fairly explicitly in a paper I wrote with Pizzo, where we looked at discrete time to in fact come up with very simple calculations. But the results in that paper survive the limit where you let the time step dt tend to zero. The ETH approach that I sketched here for non-relativistic quantum theory can be extended to relativistic quantum field theory. The analysis by Buchholz of the Huygens principle in QED implies the principle of declining potentialities in the relativistic theory. However, the details of how the events are generated and so on are pretty subtle, and I cannot pretend that everything is completely understood. So I would say the handwriting is on the wall, but some of the details should be worked out with more precision. In fact, I tend to think that ultimately gravity will come into the picture when you extend the ETH approach to relativistic theories. All right, now I would like to conclude this talk, which after all takes place at the beginning of a new year, by expressing some hope. I would like to express my hope that all major powers leaders will return to a path of negotiation and peace. In particular, since I'm stationed in Europe, I hope that Western Europe will welcome back, among other peoples, the Russian people in the European family, and that all European countries will attempt to solve conflicts by negotiations rather than by war, and that they will work for trust and peace and for the future of humankind rather than waste absurd amounts of money for rearmament. And I hope that, I'm an old man, I'm almost 80 years old. I cannot do very much anymore, but I hope that young people will become active and simply refuse to participate in the nonsense of war and of armed conflicts. That's my hope for 2026. I would like to thank you for listening, and of course, I'm happy to take questions now.